Yes, I can hear you. How are you? Can you hear me? Yes, fine. Yeah, I'm very sorry. I completely mixed up that time.
Okay, sir, no issue, no issue. Sir, good morning. That on behalf of the organizing committee of the Sswc 2025 and the GIS College of Engineering, I welcome you once again. That today that you have the first session, this is the keynote sessions one for the 2 days. Sir, I request you to present your session. Over to you, sir.
Okay, thank you. So, everyone can hear me in the conference?
Yes, sir. Sir, there is the other professors are also there, the other research scholars are also there. All are assembly. Sir, I will show you the hall. Okay. That, sir, I hand over the session to our one of my colleague who is anchoring the session. That her name is Monali. Monali will introduce you, and sir, I hand over to her. Okay, sir. Thank you.
Okay, thank you.
Good morning, sir, and good morning, everyone. So, we begin day 2 with the keynote speech of Professor Sswc Bhattacharya from University of Maryland. Dr. Sswc Bhattacharya is a professor in the Department of Electrical and Computer Engineering at the University of Maryland, College Park, with joint affiliation in the University of Maryland Institute for Advanced Computer Studies and Maryland Crime Research and Innovation Center. He received his PhD from the University of California. His industry experience includes roles at Hitachi America Semiconductor Research Laboratory and Cook and Associates. He has served in distinguished visiting positions at Temple University in Finland and at INSA Venice. He is a fellow of IEEE. Now I am requesting Sir to present his speech. Sir, please.
Thank you very much. You can hear me?
Yes, sir, we can hear you.
Okay, and how much time do I have?
Sir, 30 to 40 minutes, sir, as you wish. 30 minutes actually.
Okay, thank you. And I just need a few minutes to find again.
Okay, sir, sure. Yes, sir.
Share my screen.
সমস্যা ধরাবে
Just want to share the screen on the
Sir, once you please check screen sharing option.
Please say to share Google's screen and system audio recording. Do you have Zoom? Do you have Zoom?
No, sir, we have the Google Meet options are there.
Okay. I wonder if I email the slides to you, you can share.
Yes, sir, yes, sir. Yes.
Okay. Just send to you this was-
Okay, sir, 1 second.
Is it okay? Did you receive?
Yes, sir, I have received. I just sharing, sir. 1 second.
It's a different topic than what I said earlier.
Sir, is this visible to you?
Yes, it's visible.
Okay, sir. Okay. Sir, according to your directive, we are changing the slide, sir. Okay.
Yes, okay. Okay, thank you very much. And I'm very sorry because I made a big mistake in calculating the time difference. And so I thought the talk was tomorrow evening for me, which, yeah. And the original topic I sent you, I was going to spend some time today to prepare that. But I didn't have time to do that, so I'm talking on another subject today. Not the abstract I sent you, but this topic I'm talking about today is also a major area of my research, so I hope it will be interesting to you. And I think it's also related to the conference theme. And so thank you for joining the talk today. And my presentation is on the topic of data flow modeling, data flow models of computation, and particularly how to generate the software embedded software for smart systems and other types of embedded systems, how to generate it efficiently from data flow graphs. And my main goal in the talk will be to give some background about this area of data flow-based modeling and design for signal processing and machine learning systems. Okay, and next slide, please. Okay, and then now we have some animation. It might be easy, yeah. So, main motivation for this work on data flow. Data flow is a new kind of computing paradigm. Actually, the paradigm has been there for many years. It started being researched in the 1970s, actually, but it has become more and more popular in recent years as systems become more and more complex, and we need to look to more advanced computing paradigms beyond the conventional paradigms like those that are behind the conventional programming languages like C and C++ and Python. So a main motivation for this is because of the new kind of constraints and challenges that we have in embedded sensing systems and other types of smart systems that have very complex hardware and software configurations that have to control them, and also that have very diverse kinds of design metrics and complex trade-offs that they have to be implemented under. So to address all of these challenges, we need to look beyond conventional programming paradigms. Next bullet, please. Next bullet, please. And so, some major goals of this work is to develop higher level design abstractions with compact ways of modeling the system. So if you think about the conventional way of developing embedded systems and other types of embedded software for smart systems, often we're talking about hundreds of thousands to millions or even tens of millions of lines of code in some programming language like C, C++, Verilog, VHDL. So at one time these were considered high-level programming languages, but nowadays we're talking about millions of lines of code. It's extremely time-consuming and extremely difficult to analyze such complex bodies of software. So it's important to pursue higher levels of design abstractions to help to get a more compact but precise view of the system when we're designing it so that we can analyze and optimize more effectively. And that is what the principle of data flow that I'll be talking about is centered on. And another important concept is the one described at the last bullet here, which is the separation of design concerns. This is another important way to handle complexity in system design. So in system design, we have many different kinds of design concerns that are traditionally tangled up inside each other. And so to optimize them, it's very complicated because each concern interacts with other types of concerns. And when that's coupled with these millions of lines of code, it becomes just infeasible to do any type of powerful optimization. And so separation of concerns is a very important concept from software engineering that we want to try to apply in this kind of system design. And in particular, there's 4 important parts of kinds of separation of design concerns that the methods I'll talk about help to provide. This is separating the concern of data flow modeling, which means modeling the overall way in which data is flowing throughout a high-level application design. That's one important design concern. Another important design concern is how each of the individual modules, which we call the individual modules, we call them actors in data flow-based design. And these individual modules or actors, how to implement them individually and optimize them individually is another design concern. Another important design concern is that of scheduling. Scheduling means how do we decide which processors the actors execute on, and how do we is executed in different processes. That also affects all these implementation metrics like power consumption and throughput and memory requirements, cost, fault tolerance, and things like that. So schedule construction is another very important design concern. And finally, how do we adapt the system, the parameters of the system if we have some kind of adaptive smart system like an online learning system that has many parameters? How do we decide how to adapt them? How do we decide how much resources to allocate for system adaptation and how much resources do we allocate to the actual execution of the system? This is another important design concern. So what I just described there, 4 different major design concerns in the design of smart systems. And in the conventional way of designing systems, it's just infeasible to optimize these effectively because all of these concerns are tangled up. And the methods that I'm talking about here are a new paradigm for high-level design that helps to separate these design concerns so that we can optimize them more effectively. Next slide. And another way to describe this problem is that we have the implementation gap. One more click, please, and we can get the entire picture. One more time. Yeah. So the data flow-based methodologies that I'm talking about help to address what I call the implementation gap, where applications are getting more and more complex, more and more millions of lines of code in typical applications. So they're getting more and more complex, and at the same time, the devices onto which we are mapping these, the low-level programming environments and the associated devices, they're also getting more and more complex with more and more transistors, many different kinds of processors. And so as each technology generation goes by, it becomes more and more difficult to exploit the full potential of today's algorithms and also to exploit the full potential of what the hardware actually offers. And we're far from being able to achieve optimality in either dimension because this implementation gap keeps growing. And a major tool we have to help address this implementation gap is if we can raise the level of abstraction effectively, so we're not just analyzing at the level of millions of lines of code, but if we can have some more formal and more concise representations, which is what I'm talking about. Next slide, please. Next one, please. Yeah, you can just show all of the bullets. The main point here is that I just showed some dimensions of complexity, which is that you have very complex applications nowadays, more and very complex algorithms, billions of lines of software code, and also more and more types of processors. But also in smart systems, there are also many types of design metrics that we have to consider. So the space, the design space we have to consider is very complicated also in terms of the evaluation metrics and exactly the particular trade-offs that we're interested in. Which of these metrics is most important, and the relative importance of these metrics varies greatly from one application to the next. And so to also do an effective design, we need to be able to navigate this complex, very multidimensional space of many metrics. We need to be able to navigate that space very efficiently, and again, that's another reason why we have to raise the level of abstraction. And this situation is captured very well by the famous quote from a famous philosopher and economist, where he observes that there are no, in these such complex problems, there are no solutions, there are only trade-offs. So we need to, as system designers for embedded and smart systems, we need to be able to find not just a correct solution, but we need to be able to find the one with the trade-offs that are most strategic for our particular market or application that we have. Next. Next slide. And this is just overall outline. And so my main objective was to motivate the need to raise the level of abstraction. Then I'll talk about this concept of data flow-based design methodologies and give and emphasize the definition of this. And I think so. This talk is generally much longer than probably what we have time for today. It is the basis for some short courses that I give sometimes. Probably in this presentation we'll be covering just the bullet that's in red here. The core definition of data flow-based design methodologies. That's the main message of this presentation, and that's what I'll be talking about next. Okay, next slide, please. Yes, so this is just an overview of my research group at the University of Maryland. I have been a professor there, leading a research group for many years, since 1997. So, my research group is called the DSE-CAD group, that stands kind of in reverse order for computer-aided design for digital signal processing systems. So we develop design methodologies and associated computer-aided design tools to aid in the design and implementation of complex signal processing systems. And in recent years, our emphasis, just like probably many of those in the audience here, emphasis also has been shifting towards applications related to machine learning. And machine learning and signal processing have a very big intersection, and so my research has transitioned naturally into many types of machine learning. So the central methodology we have been developing in my research group is that of data flow graphs, which is the central theme of this talk. And data flow is for signal processing and machine learning applications. Data flow turns out to be a very useful type of abstraction to apply on top of the conventional types of programming models to give us a more compact but also very precise and formal representation of applications and system design that we can use to help bridge the implementation gap, and we can use it to also help navigate these very complex spaces of trade-offs. So what do we mean by a data flow graph? I mean that the application is represented, instead of the application just being represented as a sequence of lines of code in programming language like C or C++, instead the application is represented as in terms of a directed graph or a block diagram. In computer science, these block diagrams are formalized by a discrete math structure called the directed graph. And the blocks or the vertices in the graph for data flow represent computational modules, like they may be fast Fourier transforms or stages of a classifier, like a layer of a deep neural network. And they can have arbitrary complexity within them, but the main point is that in a data flow graph, the vertices or the blocks in the graph represent computational modules or functional modules, and the edges or the connections between the actors, these represent first in, first out buffers for communicating data as they pass from the output of one computational module to the input of another. And the data, as it passes on these flows, is abstracted in a unit that we refer to as tokens. So as actors execute, they produce and consume tokens from the edges that are connected to them. These tokens can contain arbitrary types of data, integers or vectors or matrices that the abstraction is very flexible in that way, tens of different dimensions. It doesn't, but it can be very helpful at a higher level to be able to reason about the system by just reasoning in terms of tokens, without worrying about what specific values are inside it. That's what this abstraction of tokens is in data. And then another key point about data flow is that the actors represent discrete units of execution. So instead of being like continuous processes in some multi-threaded digital filter that takes in one new sample and produces the new one new filtered output. So the computational modules or actors in data flow represent discrete units of execution. Each of these units of execution is called an actor firing, and this terminology is inspired by the terminology associated with how neurons fire in the brain. So, yes, so data flow is the essential principles of data flow. Several of them are summarized here. That it's a directed graph, and in terms of the computational modules, and these the vertices representing the modules represent discrete units of execution of those modules. Next slide, please. So then we can just look at some practical examples of data flow graphs relevant to smart systems. This is an example of a machine learning pipeline for IoT systems, where you will have some sort of federated learning going on, and then the data is being collected from different sensors and being sent to different for distributed training on the devices. And this can all be represented very naturally in data flow because of its great flexibility in being adapted with different types of tokens, different types of computational modules, different types of communication channels. We can model everything from the sensor processing to the sensor platforms to the aggregation and the training, any centralized type of functionality for training and distribution. Next slide, please. And this is another example in data flow where we can model what we call elastic neural networks, where the idea is that you can have neural networks which themselves can be modeled very naturally in data flow. And then we can also incorporate lots of other sophisticated types of ways of managing the data flow in neural networks. For example, we can exit early from the network. And by exiting early from the network, what we mean is instead of executing the entire network, we take the output from some intermediate stage of the network and apply a classification layer there, or some final layer there, and take the output from that intermediate layer, ignoring the rest of the layers of the network. And by doing this, we can trade off the execution time and energy consumption with some amount of accuracy. But if we design these exit points carefully, and train the network carefully, we can often, with just a small loss of accuracy, we can save a lot of energy and a lot of execution time by taking some intermediate point of the network. And also we can do this adaptively by changing the exit point as the system executes. So this is also something that can be modeled very naturally in data flow. Next slide, please. So those are just to give a few examples. So one great power of data flow is it's extremely flexible. You can use it to model numerous kinds of signal processing and machine learning systems. So you get this very formal graph theoretic representation, high-level representation, and it fits very naturally with the conventional models because inside these data flow blocks, like inside an actor, you can have the functionality written in any language you want, like C, C++, Verilog. You just need to make sure that at the interface of these modules, the communication follows the rules of data flow. This can be done through carefully constructed application programming interfaces. So what are some other key of data flow? And actually the key fundamental principles of data flow can be stated quite compactly, which makes them also easier to use and apply in practical design processes. So a key principle of data flow is that it's a data-driven execution model. And this is very different from like a conventional programming, like a C, C++. All of these are based on what we know as the von Neumann computing model, which is a control-driven model. In that model, actually, the programmer needs to specify not just what operations have to be performed on data, but also the order in which they need to be specified. The programmer explicitly gives the sequence of statements to execute, And if there's some kind of control flow, the programmer explicitly specifies it through things like if-then-else statements and while loops and for loops and things like that. In data flow, actually the programmer is responsible just for specifying the operations and how they communicate data. Beyond that, any of the control flow, like whether it would be any kind of iteration or conditional branching or which operator executes after another operator, or even which resource the actors execute on, this is not specified by the programmer. This can be left to other stages of the design, thereby promoting this powerful concept of separation of concerns, which I mentioned before. So this is because data flow is what we call a data-driven execution model. So in a data flow, an actor can fire not when the programmer specifies that it fires. Instead, an actor can fire whenever it has sufficient data on its input edges to perform one of its discrete units of execution. And if an actor can fire at any given point in time during execution, we say that the actor is enabled. And the actual order in which actors fire and also the resources on which they execute is not part of the specification of the program. It's not part of the functional representation of the application. Instead, the schedule is typically determined by the compiler, the hardware, the system designer, or some combination of these things. But the important point is that the order in which the actors fire and the resources they execute on is clearly separated, again, based on this principle of separation of concerns. It's clearly separated from the application functionality. And that separation is extremely powerful because the order in which actors fire and the resources they execute on, these decisions actually greatly impact most of these critical design metrics that we're interested in, things like energy consumption, peak power consumption, memory requirements, latency, throughput, and all sorts of other important metrics are very powerfully affected by these kind of scheduling decisions. And so by not tangling them up with the basic functional specification, we make it a lot easier to enable, we make it possible to enable system designers to explore different kinds of design trade-offs much more efficiently and in a way that's much less prone or much more prone to developing reliable code rather than introducing lots of bugs through dealing with some sort of situation where all of these different concerns are tangled up with one another. It's a much more clean framework in which designers can fine-tune the functionality and adapt the functionality and at the same time optimize the performance in terms of different objectives. Next. So a key part of this then is the problem of scheduling, which is this part that I mentioned is separated through the separation of concerns. And so to execute a graph, we need the graph, and the graph representing the actors and the edges, which specifies the functionality. And then we can have one or more different schedules depending on how many different implementations we want, or whether we're exploring different design trade-offs. And so this scheduling process involves these two pre-synthesis operations, the assigning of actors to processors, and ordering actor subsets that share common processors. So this is equally applicable to many different types of architectures. You can have arbitrarily heterogeneous architectures, like some system on chip consisting of some FPGA logic and multi-core processors and a microcontroller and maybe a GPU subsystem. Or you can map this kind of framework all onto just a single microcontroller. So because this operates at a very formal and flexible model of computation, it can be adapted to different platforms by adapting the constraints under which we do the scheduling. So the scheduling objectives can be can be very different depending on the different design trade-offs that are important to us. And also depending on the different platforms that are available. And so the scheduling, by iterating through different schedules, we can gradually, iteratively optimize a system efficiently for a particular platform. And also by developing multiple schedules for the same application graph, we can develop different implementations that are targeted to different types of trade-offs. You may have, for example, a company developing smart system products might have a high-end version that costs a lot with very expensive resources where the schedule is optimized to run very fast on these different resources, and another one may be designed for very low cost, where you need a very different type of schedule for the same application graph, for the same data flow graph functionality. You need a very different schedule to fit on a very small processor at a very low cost. It might be much slower, but it's much cheaper, and you can sell it for a different range of products where cost is extremely important. So these kinds of different versions of implementations can be developed and maintained very efficiently through this kind of inspection. So this is the key point I wanted to introduce in this presentation. It's a very vast topic, actually, the literature on data flow, and the importance is growing very rapidly. You can see this like tools like TensorFlow, for example, by Google, machine learning tools have been using data flow for some time. These are specialized forms of data flow that are geared towards the key sort of more general purpose kind of areas that the tool developers that develop these are interested in targeting a broad market. But through understanding and optimization of data flow principles, designers also have a lot of power to really specialize implementations in various ways for specific applications, or for much narrower classes of applications, or much narrower class of platforms for particular smart systems kinds of deployments. And that's a very important area for research that I wanted to sort of introduce the audience to in this presentation. So with that, actually, I would like to conclude. That's my, to conclude the presentation. I think I have a lot of time, and I appreciate everyone's attendance, and I appreciate you bearing with my mistake in the time planning for this. Thank you very much. If there are any questions, I'll be glad to answer them.
Thank you, sir. Thank you for your wonderful sessions, and all the participants, research scholars, everyone has enjoyed. Sir, there is because this is a digitally we are connected, for that reason we cannot share the small token of appreciation, small memento we have prepared for you, that we are sharing through the digital platform. Kindly accept on behalf of this organizing committee. So I am sharing.
Thank you, and I'm sorry, I would have loved to be there in Pulani to be.
Yes, sir. Sir, kindly accept this is a small token of appreciation.
Thank you very much.
Thank you, sir. Thank you. Thank you, sir. I will connect with you through the mail. Okay, sir.
Okay. Thank you.
Thank you,
Have
sir.
a nice day.
Thank you, sir. Thank you, sir.
Now, we are moving to our next keynote session. Our next keynote speaker is Professor Paolo Simcarini, Professor of Computer Science at the University of Bologna. He is a senior academic leader who has chaired major programs and PhD school in ICT and currently coordinates the university's research evaluation panel for computer science and engineering. I would like to sir to kindly deliver his speech. Sir, please.
So, good morning. And thank you for... Okay, there you go. Do I have also microphone? Well, because I like to move around, so... I hope that my lecture is not so boring for you, because I'm going to talk about chess. Can you play chess? Oh, you know that chess was born in India. So, if you are Indian, you should know chess. But if you don't know chess, you should at least know some old game that's called Chaturanga. It was the initial version of chess. Chess is very important in computer science, as I will try to show. And it's still important today, even if in computer science it was used since the beginning, as I will show. And today is in some sense rejuvenating. It's still very fashionable to pursue research on computer chess. In any case, I will try, since there are so many students, to give some historical context about the game in artificial intelligence and the role of the chess in artificial intelligence and computer science. And then I will try to talk about some newer research on using chess in large language models. You know ChatGPT? You know what is chat? Oh, everybody, much more than chess. Very good. I will try to show you that ChatGPT is not so good in chess, even if it is an advanced artificial intelligence model. And I will try to explain why it is not so good, and what we can do to improve the intelligence of ChatGPT, especially as a fusion work. So, I start by saying that computer chess is one of the most ancient and well-researched artificial intelligence topics. We can say that computer chess is even more older than artificial intelligence. The research history is going back to two fathers of computer science who are Claude Shannon and Alan Turing. Do you know these names? Claude Shannon and Alan Turing are considered the fathers of computer science and artificial intelligence. Maybe you know also that chess apparently is a solved game, because in 1997 the IBM supercomputer Deep Blue, so well before most of you were born, Deep Blue defeated the world chess champion Garry Kasparov under tournament conditions. So since that day, in 1997, chess was considered as a research topic, a sort of solved the problem, but it's not so. In 2016, a program called AlphaZero was based on deep learning, defeated an open source program called the Stockfish 8. It is a classic program based on polynomial evaluation and tree search algorithms. I hope that you know this terminology. Since 2023, since large language models entered our daily activity, especially at the university, schools, and so on, chess is used to test the capabilities of large language models. Okay, I will show you how. But let me start from the beginning. I'm very fond of chess because I'm a professor since, because I was interested in studying chess when I was a young student. And since chess was born in India, in some sense I'm very grateful to be here today because in some sense I'm a professor of computer science and artificial intelligence. Also thanks to the Indian culture, which generated chess. Anyway, Alan Turing is a very famous scientist in computer science, a famous prize, the Turing Award is devoted to his memory, is the most important award in computer science and artificial intelligence. In 1949, he was interested in understanding and investigating if machines can think. And chess was used in his papers to try to understand if a machine able to play chess could be considered a thinking machine. Instead, Claude Shannon, more or less in the same years in America, he was building a hardware chess machine, while Turing was more interested in software machines. So, more or less, 75 years ago, by the way, 75 years, I understood that it was also the anniversary of JIS University. So, more or less, they were born in the same years. Turing was studying machine intelligence and used the chess for his very famous Turing test and developed since then computer science theory that is also the basis of artificial intelligence. Shannon was more engineering guy, showed how to program a computer to play chess in a famous paper in 1950. He built a playing machine and proposed two possible strategies to play. One by brute force, meaning that you explore all possible moves and try to find out which is the best one. This is very mechanic, but it was very effective. It was the basis for the victory of Deep Blue on Kasparov. By the way, I hope you know that the world champion is an Indian these days. He's more or less probably younger than you. Gukesh won the World Chess Championship last year against the Chinese team. But I'm talking about machines, not about people, even if, of course, machines are built by people. Do you know who is Ken Thompson? Ken Thompson. Unix, the most famous operating system that now we know as Linux. He was also very interested in computer science chess, and in 1980 he built the first hardware machine. It was called Bell, that at the time was the first machine to win a game against a master. Then in 1997 I mentioned the one in Philadelphia by Deep Blue over Garry Kasparov. This was an event that made the first pages of most dailies, papers all over the world, because it was a very impressive victory of artificial intelligence. And that's it for the history. An important point to know, for understanding what I'm going to talk about, is that in chess there is a rating scale used for humans that's called the ELO score. What is the ELO score? It is a rating. It is points that you gain winning and lose when you lose some game. So this means that every chess player has a number associated which says how strong he or she is. Okay? The intriguing, very interesting point of ELO score is that you can apply the ELO score not only to humans, but also to programs and to machines. So this means that you can use a unique metric to compare how good is a chess player, be it a human or a people, or be it a machine. And this was very helpful to understand how good were research to improve computer chess programs. So the ELO rating was introduced 50 years ago in America. ELO is not an acronym, is a professor of statistician, who invented this rating score that was applied also in other sports. You have a similar rating also in tennis, in soccer. You can apply the idea to teams, but this is something that is outside my lecture today. What is interesting is that if you try to plot the progress of strength of chess machines along the years, you get a clear improvement. This picture is taken from this publication that I have in the slides as links, which shows how not only the progress of strength compared to computing power is L of points. For instance, here is Kasparov, that is a world champion at this level, and until 1997, the machines were able to cross this target. And now, more or less, machines are here, while the world champion more or less remains around this level. So the human strength remains at the world championship level more or less constant, while the machines go on and go on. This happens because chess is not a solved game. We don't know how to play perfectly chess. Instead, other games, probably you know tic-tac-toe. It is a very simple game that you play when you are a child on a board free. That is a completely known game, completely solved game. Draughts is another game that was solved more or less 25 years ago in Canada by Jonathan Schaeffer and his group. Instead, chess is not solved because his solution space, the number of possible games is so huge that it's impossible to search completely its game tree. So it's still interesting to play for humans, but it's also still interesting to try to build the most powerful chess machine because we don't know how it is a perfectly playing chess machine for the moment. But this is less important. Compared to the idea of resuming human progress in the same way, this is a very impressive idea because it was at least, I think, the first and possibly still one of the few fields in which you can try comparison of intelligence on both machines and humans. And this is quite important, I repeat, especially for research. An important point, engines scale with computing power, brute force. Humans do not. Okay? This is a very important point, not only for chess, but also for other fields. Yeah. But let's focus on chess. There are a lot of people who are collectors of chess programs, and they all the time spend a lot of the time comparing current programs. Probably you remember that I mentioned that Kasparov and Carlsen, over time, more or less, they have 2,800 points. I am almost a chess master. I have 21 when I was a player, 2,100 points, so I'm much weaker as a rating. But the best machines are 3,600 points. This means that no human can play at that level. Algorithmic, not only algorithmic, but also programs based on machine learning since the last 10 years, they play at this level. Okay? This level was reached with a sort of jump, more or less 20 years ago. But then this guy is Kasparov, this guy is Magnus Carlsen, who is considered the best human even these days. He left the World Championship 3 years ago, but is still playing. And now let's try to enter in the real topic of my talk. So, chess engines are too strong for humans. No way to play. This happened almost 30 years ago. Some humans tried to play, but there is, by the way, just I think 3 or 4 months ago, there were some attempts to play by humans, very good humans, having some advantage. For instance, 1 knight, 1 piece more, but the machine would win anyway, even having less material. So really, there is no game between humans and machines. However, you can use as a coach. The younger generation of chess players, especially in India, they are very good players, even also because they had a lot of familiarity and use of computer chess programs. The problem is that the chess programs are very good, but are very bad as coaches. They do not explain their moves. They play the moves that are strongest, but cannot explain to humans why they are good. So the idea is to try to introduce large language models in the loop, so to speak, in the conversation between humans and programs using large language models. If you know the field, there are literally thousands of chess programs. It is an exercise of first year in computer science degree to write a simple chess program that usually is not so strong, but of course it depends for its strength from the underlying hardware. So writing a simple chess program is a first year exercise these days for computer science students. The best chess engines, on the other side, are the result of several years of improvement and experiments. Stockfish, the most famous open source chess engine, was released initially in 2008. In this year it is version 17 and is written in C++, open source, completely free, and is currently engine number 1 by L. It is also interesting from a software engineering viewpoint because there is a special platform for testing new versions that's called Fish Test, and it is very, very interesting. I want to stress a little bit the difference between all the time deep blue-like programs and modern programs. Until, say, 10 years ago, was typical to have programs based on polynomials. Polynomial including some counts, for instance, material count, space count, evaluation of king safety. The most complex programs could have 200 factors in the polynomial. Instead, since Alpha 0, 2016 I repeat, we have chess machines which include models based on machine learning. So for instance, in Stockfish now you find a sort of black box that's called an NNUE. NNUE stands for Neural Network. Neural Network, anyway, a neural network has a completely different structure from a polynomial, and it is built training the model either in self-play or using huge databases of games from humans and materials of other machines. In any case, I don't want to enter the mechanics of machine learning. What happened 10 years ago was a sort of quantum leap for Stockfish, which suddenly progressed a lot. You see, normally these machines, these programs, improve very slowly because the programmers try to squeeze any kind of computing power, improving the software. Instead, using machine learning, there was a jump in strength that since then continued, and this day Stockfish is the strongest program, even if also other programs include machine learning elements. Stockfish, as I mentioned, has a number of limitations. Stockfish is very strong in matches against other machines or in humans, especially if you play, for instance, 1 minute, 3 minutes, 3 minutes for the new game. But for some unbalanced cross positions that are especially interesting for humans when they play, is not so useful. It makes, if you try to learn chess, especially a strong level, against Stockfish, you can use a special handicap mode. That means that it plays errors randomly. This is considered useful, but it's not very so useful to because random errors, of course, needs to be explained. In general, the score given to modes of position by Stockfish is not completely clear and aligned with the human literature. If you know chess, realistic chess, there are literally thousands of books which comment games, which try to evaluate position and so on. And in general, there is no way to have a conversation on a game with Stockfish because it's not a large model. Instead, a large language model is a deep neural network model which has been trained on large amount of text data, and so the text data includes, for instance, books, software, papers, websites, huge means billions and billions of these data. And so we have powerful models that you know under the names of DeepSeek, ChatGPT, Claude, etc. There is a special variant of large language models called reasoning large language models. You must never forget that per se large language models are based on some stochastic behavior. So they basically tell things that are probably good to say, not true, but good to say according to some frequency that they found in literature, okay? When you have a reasoning element, there is an attempt to let them to reason about what they say, okay? So chess is interesting because chess is a language, and the game is a conversation actually. By the way, this guy is the current Indian world champion. Instead, this guy is a Chinese that was a world champion before him. Why I show this? Because if you know chess, you know that games can be transcribed. And so there are a lot of databases including not only the moves, but also comments by humans. And there are literally thousands of books. I'm a collector of books. In my small collection, I have 3,000 books. But the estimated size of chess literature is 100,000 books. There are libraries in Cleveland, Ohio, in Amsterdam, Netherlands, in which there are much more than 50,000 books, and so the literature is huge. What do ChatGPT knows about chess? So you ask, and you know that you can have a conversation with ChatGPT. So I asked 3 days ago, can you play chess? Yes, of course I can play chess, says ChatGPT. Not like Stockfish. This is an actual answer by ChatGPT, okay? Which calculates the forest of lines per milliseconds. But I'm more conversational, I'm more strategic. I can choose moves, explain ideas, evaluate plays, and play a full game at a speedy human-like level. Wow! Wonderful! A good coach, so I can have. You can get a good coaching, good training from ChatGPT, for free, if you know how to access ChatGPT. I'm using, by the way, the most advanced version that you can get by money. If you want to start a game, just tell me your color and play the first move. Okay, let's go on. So I write my question. After, this is a game, if you know the game, these are moves, palm move, knight move. This is in Italian, okay? So C stands for knight, these are squares on the board. And the right circle shows a move that is impossible. I made an error in the description of the moves, okay? I expected that ChatGPT corrected me. Oh, there is an error, that move is impossible. Look instead at the answer. Oh, I take the classical Berlin path. Knight 44. What does to do Berlin here? There is a famous defense called Berlin defense. This is called the Spanish opening. And so Berlin is, this move would be a B5. Instead of A5, this would be a normal opening. Instead there is an error. And ChatGPT is not realizing that there is an error. Makes no sense. Okay? But in any case, it's gone. Why? Because it has to answer in a most likely way. It's lying in some sense. It's too big to answer this way because this is not a correct fragment of a game. And even the suggestion, choose the rook A1 or sharp and move, is trying to suggest moves. But my point is that there is a basic error in this conversation that we cannot use to go on. Even worse, even something that would be very useful but does not work. Do you know that you can feed a PDF to ChatGPT to get the content, examine it, maybe have some answer? You can put an exercise in PDF, written in PDF, and ask, please solve this exercise. I tried this experiment. If you are blind, this is very important. This is a game, normal score, with this diagram. So this is the game in international language, which the pieces are represented by figurines. Here there is the chessboard, the position of this letter. If I did this, putting the PDF, probably it was not PDF but PNG, but it was an image that they put inside ChatGPT and asked to describe the diagram. That is very useful, for instance, for a blind person. Okay? The description of the diagram was completely wrong. If you check piece by piece, all the red circles are errors. Why there are errors? Because large language models are not precise. You cannot expect a perfect interpretation of any document for them. Okay? So it's normal for them to lie. They are called hallucinations. And in chess, there are a lot of hallucinations because they don't know how to play chess. They simply use frequency of text, quoting some, so probably they have in their memory some position which has actually these pieces in those positions, which do not correspond to the reality. Okay? This is terrible. It's terrible because in chess we have a long tradition of literature. We have a lot of, for instance, specific techniques to define positions, not only graphically, but also, for instance, textually. If you know the term serialization, there is several techniques for serializing chess games. For instance, a famous technique is algebraic concurse. This is algebraic description of a game. Another possibility is called the Forsyth-Edwards notation, by which these strings are too small for you to see, but basically you describe row by row the content of the chessboard. And this is the description according to this coding of a game one between Bukash and Wimbledon for the World Championship in 2024. Okay, why am I showing you this? Because the foresighted word notation, that is a mathematical description of chess game, is completely very difficult for them, for larger models to understand. And there are a lot of studies using this kind of notation, those notations, to test how good are large language models when dealing with the chess games, chess fly. This is a recent paper, 2025. Again, it's too small, but you can find it is in archive, quite recent. What are the blue and the red? The blue are non-reasoning large language models trying to play chess. And the orange are reasoning large language model, applying some logic in their attempt to deal with chess. What is the black line? The black line is the performance of a random player. A random player in chess is a player who or which plays random games, random moves, without any thinking, okay? So this means that all non-reasoning LLM are worse than the random player. If you want some hope to have a chess playing behavior, a reasonable chess playing behavior from a large language model, you need to have reasoning. So this is something very interesting, don't you think so? But still, it's not, I'm not concluding. I still have, I hope, 10 or 15 minutes, so I go on. So the point is that chess, for the moment, is a very good benchmark to understand how good are and how reliable are our large language models in this moment. How are reliable? Nothing, zero. If you use a normal large language model, this means that they are worse than random players. So this means that you must be very careful when you ask something to ChatGPT or similar without applying the reasoning and get some result. It's still wonderful that they can write programs. This is a different topic that we can discuss another time if you invite me. But in chess, you should try to avoid to get suggestions from large language models, because these suggestions are completely useless. So this is called to make benchmark. An interesting point is that the benchmark that we are using define what intelligence means for a model. In some sense, they are compass that we use for our research to try to understand if you are doing well in our research. So a principle that is quite interesting is that you get what you measure, the metrics shape the model design, and many classic benchmarks that you can use in large language models are typically saturated, is the term. Means that the large language model can be trained to have good performances in these metrics, okay? And so they are useless because you invent a metric and you can also try to change the behavior of the model to have a good performance and to the metrics. In chess, this is yet not happening. And so reproducibility and comparability using chess is especially still very popular. But what is chess as a conversation, in which sense I wanted to show you the last part of my talk. And chess engines, algorithmic or based on machine learning, are superhuman, but hard to understand for humans and to imitate, to simulate their behavior. On the contrary, large language models are very good at talking as language, but Struggle is a very under-evaluation of what they do. They really cannot have any reasoning. So our idea in my research group is to combine the precision of engines with the clarity of large language models. In some sense, we are using a concept that is very popular and fashionable these days. The research called agentic LLM. Agentic means that you try to constrain the behavior of a large language model, which has to ask for help to an external entity which can guide and improve the answers of the models. So for instance, in this picture taken from this paper, again, you see the papers that I mentioned are 2025, so very recent. You can try to ask to an external entity, an expert model, for some chess knowledge, and the large language model adds some language, some conversation that can be useful for a human. So we asked ourselves, how can we improve the quality of large language models and comments? We have developed for the moment a couple of models, but based on a theory developed by a chess master called Alexander Shashin, who developed a theory of chess in which he tried to explain the complexity of chess as a complex system, and introduced a jargon in defining the strategies that are available to chess players. Sorry. I can use it this way. Yeah, I can move, I like to move. Alexander Shashin is a master of chess, a master coach, and also physics. I think he has a PhD in physics. And he defined chess as a complex system, introducing a sort of mathematical model that apparently is similar to the algorithmic approach. However, he's also introduced the language we talk about Tal positions. Tal was an important, they are all world champions. Tal from Russia, Soviet Russia, Capablanca from Cuba, Petrosian from Armenia. And Tal was a strong attacking genius, Capablanca was a strategist, Petrosian was a good defensive players. Shashin gave 5 factors: material, relative mobility, safety, density of a position, and expansion factor of the position corresponding to a constant potential and energy. These factors all correspond to some mathematical formula that I have no time to introduce. So you still have some mathematics basis for this approach, which can be translated in chess language. We have developed a program called the Chess. It is a combination of Stockfish with Shashin theory. Especially interesting are, according to Shashin language, positions which are chaotic, which are especially interesting for humans, because humans in this way can understand the mood, the style, and the position, and there are, players who are attackers, players who are best defenders, and so on. And this way, the language introduced by Shashin in his books, in his book that is mentioned in my reference, can be more clear for humans. So this is the book called Best Lie. It is 2010. And okay, these are example positions in which the material is computed as the ratio between the white material M1 and the black material M2. This is the mobility, that is again computed as a ratio. This is safety. This is density, if I remember well, and so on for all. This is an example of a chaotic position according to this theory, just after 2 moves for white and 2 moves for black. What do you get with Sswc compared to stockfish? Well, basically Sswc is derived from stockfish. However, there is the possibility of having some more information in the evaluation of the position according to this theory. To make a simpler, to make simple and more complex, a number of more complex ideas, what we have here is, sorry, this is out of order. This is again a comparison of the ability of reasoning models compared to non-reasoning models. So reasoning means that you can apply some pattern of logic reasoning in evaluating a prompt. And we exploit the Sswc theory in a reasoning system that we call the Sswc, which combines the output from stockfish and gives to an AI commentator that is able to reason, and then we display the moves. Okay, so we have a system which basically takes some output, asks for the evaluation to a component that is stockfish, and we get some conversation guided by the output. The conversation can be very long. You can modulate this, the way in which the large language model can answer to your prompts. These are examples of prompts that you probably cannot read. Anyway, this is a standard prompt without Sswc. This is a prompt including Sswc theory, so you see it's richer and also more useful to guide the conversation output by the language model. So the system that we call Sswc is an agentic commentator in real time, means that you can use it while the game is in progress, and is based on a combination of stockfish with llama, stockfish slightly augmented with Sswc search theory, and the llama 3, that is an open source language model. So we have a sort of agentic loop, the sensing of the position using stockfish, the interpretation by llama 3, and the answer to the user. So stockfish evaluates the position. A control module derives the Sswc prompts and extracts the key ideas. The Sswc prompts are given to llama 3, which generates the commentary, including the evaluation, the plans, and the style. Basically, we call this agentic features, which use the external tool under model guidance, keeping again context across moves and producing goal direct. We also had an evaluation, quite restricted. This is a brand new research that we applied this year. We queried some players over the internet over these positions and passed them the comments by the Sswc program, and we got some results that basically with normal prompt gets some answer, with Sswc prompts gets a much better evaluation by human players, which liked the way in which the system tried to explain the position. I skip the other mathematics. I will give you the reference to my paper, in which you can find easy numbers well explained. I want to conclude showing you a couple of pictures. This is the ancient library of my university, the Aula Magna of University of Bologna, which you see there is a chess tournament that was played 2 months ago. We invited students from all over the world, invited people from Yale, Harvard, Cambridge, Oxford, Sorbonne, Dublin Trinity, Dublin University College. There were 18 teams of humans, students. This is a university tournament. What has to do with our topic? Well, we set up, using a sponsorship from Intel, an analysis room in which you see the students, the players, after the game, they could ask the system for comments on their games. Okay? So this was probably the first time we used the AI-based room for a chess tournament. Now I want to conclude. So why chess still matters? Chess is interesting because it is a combination of symbolic precision and strategic reasoning, for which large language models are not yet perfect, are not yet good to converse, to talk about chess alone. If you try to play chess, you can do something if you have a reasoning variant of a large model, but still they're very far away from being good players and even less good coaches. So if you exploit engine evaluation, you can improve the way in which you can get information from a model. We are exploring a number of research directions, including chess commentary, multi-language. This can be very interesting because you can have one system in which you can have maybe millions of people. This is very challenging because you need the models for each language to be able to talk in parallel. You can have style, conditioning, reasoning, evaluate alignment, for instance, with attack reasoning, defensive reasoning, and so on. Future work also includes enhance the machine learning model, exploiting the experience of humans. You can try to tailor the machine model to specific humans. Actually, we are trying to help specific humans at the master level, exploring their way of thinking, so to speak, using the Shashin approach. I mentioned the multi-language language model for commenting to games in real time, or a worldwide site, for instance. We want to improve the user interface for training and coaching using our approach. My conclusion, and I finish, computer and chess research is older than artificial intelligence, and it's still very alive and exciting. I try to prove that chess is a conversation, as a game, is a conversation, and models, language models, are very good conversers, but very bad reasoners. So our solution tries to solve this problem. Our solution consists in exploring agentic language model to let them to talk and play with chess. And these are references for my recent papers that I decided to devote my last years as a professor to this. When I started studying computer science, the computers were absolutely very bad players. Now they are very good players, and I'm trying to talk with them. Okay? So thank you for listening. If you have any question, you can ask. It's your turn.
I have a question about the recent time. One of the great chess god Mitten, Elo of 9099, who recently defeated the Stockfish level 8, and also defeated the Magnus Carlsen, International Master Levi Rosman, and Hikaru Nakamura. What do you think about it?
You have this kind of players. I'm positive.
the question of what do you think about this, the recent kind of the approach of the like bots, where recently reached the year of 1999, but 2,800 crowd, they did not reach. When Ashraf say able to this kind of performance, also recently this network defeated the many more players, billion players. But it is, I think it is the harmful for the chess event or it is also destroyed as chess.
I mentioned that there is no possible contest between humans and machines. Machines are simply too strong for humans. The best humans have a performance that more or less is constant. Instead, machines, thanks to improve the hardware and improve the software, they go on continuing. So, what I showed here is more an idea of cooperation between machines and humans. You can use a machine, even if you don't have a master near you. You can ask Shashguru to explain chess, because it's very expert, very proficient in chess, combining the power of stockfish with the basic ideas in the theory of Shashi and the conversational proficiency and the power of Lama, or whatever you want to use, because it's just an idea that you can replicate, okay? So I'm sorry, but maybe I'm not sure that I answered your question. Okay? Okay. Other questions? Okay, so I think we can stop here.
Thank you, sir. Thank you for your wonderful session.
We are having an online session now. So before that, we are taking 5 minutes break, and I am requesting all the students to come back within 5 minutes or stay here, but we are having a 5-minute break. Make sure those who are going out, you will be here after 5 minutes. Make sure that. Only 5 minutes. Don't go like this, don't go. All of you don't go, stay here. If you want, one by one can go outside and come back.